Swayam Prabha. Digital India. Educated India.
Hello everybody. Well, we have been discussing so far various types of pumps, then measuring devices and little bit about conductance concepts, etc. Now is the time for us to really go into constructing vacuum chambers, flanges, couplings, so that we can make a system out of it and then finally use it and check if there is any trouble, then we will have to shoot the trouble. This is how vacuum technology goes generally. But the problem, main thing is, first you should choose a material. Without material, how will you start making a chamber? So, there must be sufficient knowledge to the engineer who is going to work in vacuum technology about the materials being used for various purposes within your vacuum system. So, today we will spend some time in discussing vacuum materials. It can be metals or alloys, some glasses or ceramics or greases or oils, plastics, etc., etc. Well, the concepts that are going to be covered in this small talk for half an hour. Of course, we cannot explain everything in detail in small limited period, but I will try my best to give you glimpses of various important points. The material properties required for vacuum technology, that will be highlighted in the beginning. Then in light of that, we will see what type of metals to be chosen and glasses to be chosen, and how do you select ceramics, any special treatment is there to make it suitable for joining with metals. Then we will see some greases and oils which have to be used up to some level of vacuum. We will also see some cheap materials, cost effective materials like plastics or mild steel, etc., when to use. In certain high tech applications, we cannot afford to think of cost, because the application is so costly. We should use only high tech materials like high quality stainless steels, etc. So, it all depends finally on the type of application and the budget you have and type of problem that you may encounter, or the level of sophistication involved in that technology. Depending on that, you have to choose the materials, and also depending on your capability to weld or join within your workshop, you should choose those materials. You cannot take very costly material and make a shabby welding or something, you will get into trouble. So, these things also we will be discussing in the next class, but today we will just only discuss the materials point of view. Once we choose the materials, then we will give some design criteria for chamber making, etc., then fabrication, then finally testing. So, it goes like that before we enter into system design in a gradual manner. So, today we will just spend some time on different types of materials involved in vacuum technology. Well, any material in a laboratory, it has to be tested first as a material, not as a component. Okay? Iron piece, that iron can be made in the form of a component, but we will have to first get an idea of its properties. With respect to vacuum technology, what type of properties we are looking into it for the materials to be incorporated in our actual application. First is mechanical properties. It should be strong. After all, under vacuum, because of elastic instability, the chamber will collapse. If you do not have a strong material or if you have chosen a wrong thickness, or if there is some flaws, there are some cracks in that material because it is a low cost material. Same stainless steel, very high grade quality, high quality can be very costly. There may be a cheap material, sometimes it may be okay. So, you should be judicious in choosing the material. For 10 power minus 2 tar minus 3 tar, why should you unnecessarily spend money? You can choose a typical steel that is available in the market, but if it is 10 power minus 7 minus 8 tar, you should immediately take other properties. What are those properties? First, machinability. Machinability is very important for any mechanical engineering operation, but in vacuum there is one additional criteria. When you machine inner side of a pipe which is facing the vacuum side, the machining should be done with high precision. That means, the surface finish at the end of the machining must be very good. You should be able to see your face, it should look like a mirror, though it is a stainless steel piece. Why? The apparent area, that 2 pi r h in the inner side of a vacuum pipe, should be the actual area that in atomic scale. That means, if some atom is trying to move, how much area it is going to cover, that area may not be the apparent area. What we see with our eye is the apparent area. So, more and more you are polishing, you will get better and better quality with respect to vacuum, because area available for degassing is less. That is very important for ultra high vacuum. It may not be important at minus 2 tar. So, machining and also polishing, they are extremely important with respect to the level of vacuum. Ultra high vacuum, that is why is very costly. That is the reason the semiconductor industries, space technology or nuclear technology or advanced in metallurgy, they are so costly. Same stainless steel chamber, but when it is applied to high vacuum or ultra high vacuum, the type of machining and polishing involved are totally different. We will see that while fabrication later. Here I am going to talk the properties only. Similarly, thermal properties. Thermal properties are variety of properties, thermal conductivity, thermal expansion, or its specific heat when it is cooling down of a cryogenic container, or its degassing at high temperatures, thermal compatibility, etc. And fine cracks, blowholes within the material, they are not allowed in vacuum, because there will be lot of trapped gas which will finally come into the chamber during your operation, which is going to be very dangerous. You will never get vacuum. If you do not get vacuum, your process will not start. Then reactions, the vessel itself should not react. There will be reactions inside for some process. If the chamber itself is reacting, then your process is total failure. So, you should also choose those materials which do not react with that particular process. As we see the applications, these points will be again covered there. Then in nuclear applications, there are lots of dangerous radiations are there. So, these radiations are falling onto the chamber. The chamber should not degrade because of these radiations. There are several other special properties which I have not covered here, but as and when we go to the applications, we will find some more properties. These are general properties, mechanical, thermal and radiation, degassing properties, etc. Keeping this in mind, let us see metals, let us see polymers, let us see composites, let us see plastics, greases, which glasses, ceramics that are routinely being used in very high vacuum technology. We will start from metals. As far as the vacuum is concerned, earlier I have seen several properties, but from vacuum point of view, the materials have to satisfy some additional criteria. What are those? This is vapor pressure of that metal or alloy, whatever we are using, either as a constructive material or as a manipulator material within the vacuum chamber, or some transducer, or whatever you are keeping inside vacuum, that everything is a material. that should not degas at the working temperature, not at the room temperature in the beginning when you are assembling it. At the working temperature, it should not degas or it should not evolve lot of gases. Little in depth, second property is, even if it has absorbed some gas when it is exposed to atmosphere, it should be possible for you to degas it easily once it is loaded inside. There are high level of degassing, then you will never get vacuum. But if you are able to degas it fast using some forcing by ion beam etching or some infrared light on or baking it, etc., you will be able to solve that or purge it with a gas and remove that, clean it, then start your application. So, it should be possible to degas it easily also. First is, it should not degas, it should not have too much of gas content. Even if it is there, we should be able to remove it. Under vacuum, if you remove it, there will not be again gas there. Okay. Generally, for high vacuum, structural point of view, even today, in future we do not know what new materials will come, but as of today, stainless steel is number 1. That too, the 18 by 8 composition, very famous composition, that is standard stainless steel, which is non-magnetic, which has become very famous in the world, because it is used almost everywhere. There are steel plants, steel industries which are trying to control the economy of a country. So, it is mostly dominated by stainless steel for day-to-day applications. Of course, there are some specialized steels, but stainless steel is most important. Why? It has got a composition which is non-magnetic, though it has got huge amount of iron, and it will not produce any stains. That is why it is called stainless steel. And corrosion problems are not there, machinability is very good, polishability is also very good. That means, you can machine it at various grades till you get optical finish. A brand new plate that we see in our day-to-day life, you can see your image. That means, the up and down, the roughness of the plate is of the order of the wavelength that is falling on your face and going there and getting reflected. That means, it is submicron level, 0.1 micron type of polish. It is entering into 2000 angstroms type of thing. Then only your apparent area will be approaching the actual area, and if the area is very less, degassing problem is less, because for a specific unit area there is a degassing which is a property of the material. If the area is much more, then you are in trouble. So, it is only the top surface that matters. Backside bulk material also matters if there is something diffusion from the back. That is a real problem only in ultra high vacuum. Up to 10 power minus 6 star surfaces matter. That is the reason even if you use mild steel, if you are able to make some specialized treatments or platings, you can use it up to minus 6 star maybe, if you can handle the corrosion problems. But stainless steel is definitely good, because of corrosion resistance. Here I have shown a small figure. CR means corrosion resistance, W means weldability, Y means yield strength, M means machinability. All 4 are important. Different grades are there, and different grades are with different price. So, if you do not require very high corrosion resistance, after all you are just a minus 2 tar application for some wastewater clean, splashing or some normal applications, let us say, then you do not have to go to this right side top corner. This is the costliest material, because corrosion resistance is also good, reasonable weldability, like that, and yield strength keeps on increasing. So, first you have to see machinability, then weldability, then yield strength, then corrosion resistance. So, different grades are there, 304, 304L, 304LN, etc. For cryogenic purposes, you use LN series. Okay. So, what is to be used is to be decided based on the level of vacuum, and if it is a permanently sealed device, then you have other requirements. Degassing should be less, because as soon as you seal and give it, within a 10 days if it is giving bad vacuum, then it is of no use. All those things have to be considered. And with minimum thickness, it should withstand the external force of 1 atmosphere. Maximum pressure difference is only 1 atmosphere in a vacuum chamber. Pressurized chambers, inside can be 10 bar, 20 bar, 30 bar. So, delta P can be variable, but in vacuum systems, once you cross 1 tar, it is delta P is only 1 bar. It will not change, but it does not mean that it is a small force from the outside, because the mechanism is elastic instability. So, it will collapse, that is dangerous. You should have some reasonable thickness. These thickness calculations we will see in the next class later. And what makes it 18 by 8 steel so popular? Because that particular thing is only corrosion resistant, fairly strong, machinability is good. But there are some problems. Carbide precipitation, this is a very famous issue, metallurgists know. I am not going to discuss more in detail, because chromium has got a role to play, 18% chromium has got a role to play, 8% nickel also has got a role to play. So, the shiny appearance is related to something, and corrosion is related to something. So, this carbide precipitation is an issue. You can look into website and Wikipedia, there is a huge amount of introduction given there. That I am not going to discuss, but this carbide precipitation results in hydrogen permeation, and vacuum compatibility is going to be poor in some situations. Okay. So, you should be careful in handling carbide precipitation. This is possible by special alloys in stainless steel, several grades like 304L and 316L etc., where low carbon steels are used. But low carbon steel is having another problem, because low carbon steel is not very strong, but you may not require very high strength. After all, structural material only 1 atmosphere. If necessary, some stiffeners can be added, that we will see in the later class. But weldability, leak tight joints, they are very important, reasonable thickness. But if you make a mistake, if you make double the thickness, cost will be double, and a very high quality stainless steel for a large chambers, as a what you call as a bad engineer, let us say, I should not use bad word, but if you are unable to calculate properly and you end up in purchasing huge amount of stainless steel, very costly. Okay. So, intelligent engineer should try to minimize the thickness, but maximize the strength and minimize the surface area. So, all these metals have to be suitably modified to match to your vacuum applications. When you look at this right side, stainless steel degasses over a period of time and finally saturates. But if you observe carefully, aluminum is the best thing, it degasses very small. Copper is next best, but we will not use copper in making vessels, it is quite costly. And on the lighter side, copper people will steal, because they can remelt immediately and use it. Stainless steel, nobody will steal, that is why it is stainless steel, because if you remelt it, unless you make exactly 18 by 8 type of thing, you will get only rusted iron, that is very cheap, nobody will steal stainless steel. But aluminum is ideal, but unfortunately aluminum welding is still a research problem. So, welding is not possible, and aluminum cannot stand high temperatures, but it is ideal for manipulated materials inside the vacuum chamber. So, different materials have got different roles to play. Copper is very good for the feed through materials, where you can pass high current from outside to the inside. There are applications for every material in vacuum, but something is in small quantity, something is in big quantity. There can be a small quantity material highly expensive, like silicon wafers, which have to be compatible under vacuum in semiconductor processing, etc. Several other things, getter materials, titanium alloys, very costly, maybe small material, but may be very costly. We will have to look into cost issue towards the end of it. Okay. While continuing the metals issue, there is one material called covar, which is very famous, with 17.5% cobalt, 28.5% nickel and rest iron. This is ideal in making glass to metal joints. I see there are many electronic components
high power electronic components. They are not semiconductor based electronic components like valves, etc., in big transmitters and radars, etc. Most of the high power electronic applications, you still have valve based electronics, triodes, diodes, etc. In such places, you will have metal to glass joining, and that is possible with CoVar because it has got matching thermal expansion coefficients with the glass. So, if you coat little bit of metallized coated glass things towards the end using some specialized techniques, we will see later when we go to the electrical engineering applications. We can have such high vacuum tubes which will retain vacuum for a very long time, years together. A vacuum interrupter sitting in the high power lines has to stand 20 years without losing vacuum at 10 power minus 7 torr, and it has got a ceramic bonded to metal caps with a huge amount of copper electrodes passing high current and high voltage, 110 kV, 3 kiloamperes at high voltages, and waiting for a fault to come. This is an interrupter, safety interrupter. 20 years it has to work with vacuum, because you cannot have opening under high atmospheric pressure, it will have a spark or arc. That is why vacuum interrupters are very useful in power systems. Anyway, in such applications, you require a combination of CoVar, copper, stainless steel, glass, etc. Brass is good, but it contains some blowholes first of all, and brass contains zinc. Unfortunately, below 10 power minus 3 torr, zinc evaporates, zinc sublimes, I would say. So, this is a nuisance. So, if you want to use brass less than 10 power minus 3 millibar, it is not allowed. Instead of acting like a chamber, it will start acting like a degassing source, which is bad. Okay? And particularly if you are crossing 100 degrees centigrade. Mild steel, as I told you, it is ideal, cheap, but it cannot be used below minus 3 torr because it may get it may produce some rusted things. Rusted things absorb lot of water vapor when it is exposed. In the next run, it will create lot of problems. The rusting is not allowed, surface finish will be spoiled. But there are some special coatings, now research is going on to make mild steel chamber, but inside it should be vacuum compatible first layer. Very good research for the startups. Then titanium alloys, they are very good. They can also be used as getter materials inside as a local pump. We have seen in sputter iron pumps, etc. These are the titanium filaments, and these are copper feed throughs with ceramic. So, there are lot of technology. It is a very costly piece, I am telling you. If a startup comes and they can make a stainless steel flange and attach it to a ceramic and then copper, pass high current, inside conflat flange, there is a metal gasket, you show to the customer, it will withstand 10 power minus 6 torr, then you can say this will be 2 lakh rupees. Otherwise, if it is leaking, it is equivalent to some 200 rupees. So, these are specialized feed throughs. There are lots of technologies behind it. Okay? These things have to be understood along with material selection. When you do that, you also have to include other materials like glasses. Okay? Glasses are ideal for you to see what is happening inside a vacuum chamber. So, that is high vacuum window with suitable flanges, and that can be coupled to a chamber. I will show you a chamber maybe later if possible. Vacuum chambers is by itself a big branch. We have got a full session for it, and there are lots of windows here and there to look into the process, what is happening inside. But if this itself leaks, then we will not get vacuum. So, glass material, ideal glass material, Pyrex borosilicate glass is ideal. It will not degas much, and it has got sufficient strength, and it can be sandwiched between two flanges with some gaskets, etc., and it can be connected to a chamber. There are glasses which are ideal for high vacuum applications in power triodes, which are now being used even now in radio transmission and even big high power electronic circuits, which depend on good old diodes and triodes, where electronics have started, even now they are used. Or typical incandescent bulbs or tube lights, etc. X-ray tubes, even though they are glass based tubes with cover seals at the end, and standard bell jars. In most of the universities you will be doing thin film technology research, and the ionization, nude ionization gauges, all these things have got glass pipes. Okay. You will have to be careful while handling glass, but glass is better than even stainless steel. It will not be able to leak much. So, that way if you handle glass properly, you can do wonders in vacuum technology. Most of the discoveries in physics, fundamental physics, they all happened in vacuum, but using glass equipment, whether it is a discovery of electron or proton or photons or all sorts of research topics, even a first bulb, for example, Edison when he made, all sorts of cathode ray oscilloscope, which is background to the TVs later, and then of course, LCDs, LEDs, bulbs. Most of it initially they did with glass. Cryogenic engineering, first of all. All the cryogenic discoveries are done in double walled glass insulated vessels only, because you wanted to see what is happening inside. Okay. So, without spending much time, let us go to the other materials. As I already told you, ceramics are stronger than glasses, but they are ideally required in interrupters, high voltages, or wherever electrical insulation is required, but they cannot be made in the form of flanges. You require flanges on both sides, which are metallic, particularly in ultra high vacuum applications like this. Okay. So, they are not flexible also, and for example, in a vacuum interrupter, which is very popular, both these electrodes, they are made to open under high vacuum with some getter sitting somewhere here as a local pump. Each vacuum interrupter is costing more than a lakh rupee. The materials and the joining techniques have to be suitably mastered, so that you will be able to make a good leak tight vacuum interrupter for 20 years at 10 power minus 7 torr. So, naturally the ceramics chosen for such applications must be of that quality, then they should be polished properly. So, there is a lot of ceramic research going on. Almost every country has got their own ceramic research institutes. These ceramics are specialized ceramics. They are not the ceramics that we are using in toilets and other purposes, because they are only meant for some mundane purposes. But the ceramics that are used here, very small pieces, are very costly, because they do not have blowholes, they do not have occluded gases inside, they are machinable, and they can be joined to the metals by diffusing some metal vapor at the edges, so that metal to ceramic joints can be made. Okay. So, all that I leave it to you. In the internet you will get lot of things on ceramic to metal joints. Okay. And machinable ceramics is a big research area by itself, and how do you make drills, how do you make holes into that, it is a technology by itself. Later, if time permits, we will see under special applications, same thing, we will come back to that. But ceramics are going to play a very important role in future, when you are going for high voltages and high energy research studies, because always you may not be able to use metals or plastics or anything. So, you have to use ceramics. Ceramics will not degas at all. Glasses are ideal, but glass will break easily. Ceramics are stronger. Now, up to high vacuum, people have got a tendency to use gaskets, white on O-rings, etc., in between flanges, so that sealing takes place. And sometimes these seals, to avoid moisture absorption, etc., you need to apply a little bit of grease, and these greases should not evaporate under vacuum. So, you should have low vapor pressure. So, these greases, vacuum greases are available in the market, high vacuum greases. They are silicon based greases, and varieties of small varieties of high quality oils are also available, which will be used in the shaft seals within the pump, or sometimes circular motion is required in a vacuum chamber, planetary motion is required, or a linear motion is required in big nuclear fission reactors, etc., where you will have to move certain things inside in a vacuum chamber. There you may have to use oils, but oil should not be having vapor pressure more than the vacuum level. Its vapor pressure should be much less compared to the operating vacuum level. Accordingly, you will have to choose that, particularly when you are using it as a lubricant or a sealant, whether it is in the form of pump oil or whether it is in the form of some sealing oil in the chamber. You have to be very careful. So, greaseous oils are also important, and accordingly you have to choose them with care. And ultra high vacuum, these are totally not allowed. Gaskets are not allowed, O-rings are not allowed. You have to use specialized components called metal gaskets, and you have to use thick flanges. There cannot be simple couplings. You have to squeeze them so that the gasket flows like a rubber at such high stress. All that we will see when we go for couplings and flanges or walls in the next class. Plastics are not really being used much in vacuum technology, but in rough vacuum up to 1 torr, 10 power minus 1 torr, you can use plastic bottles, because there are large scale applications of vacuum technology in high, relatively poor vacuum, medium vacuum, etc. We have to handle distillation, chemical, pharmaceutical applications, etc. There vacuum level is not much, but chamber sizes are big, flexibility is required, and later you have to put it in some containers. So, there is good amount of application of plastics or polymer type of bags, etc., polythene and PVC, Teflon for example is ideal thing. It is very good material. It has got self lubricating capabilities and it is fairly strong, fairly flexible. Okay. So, you have to choose them, but you will have to also see the outgassing rate. If outgassing is too high and that outgassing will produce a vapor which will spoil the vacuum, then it is of no use. But if you are using 100 torr, it will never spoil that vacuum, because outgassing is 10 power minus 5 minus 6 millibar liter per second per centimeter square, a typical bell jar or something. It may be doing lot of degassing. When pump is running, anyway it is being taken care. So, nothing will happen even though you are using plastic. So, at what time which material to be chosen, an engineer has to decide, taking finally the budget into account. Okay. Always you need not have heavy metals. Okay. These are the points I want you to understand in general: greases, plastics, seals, metal, ceramics, glasses, etc. Having understood these materials, we will see how to make components and various other devices in the next class. Okay. To conclude, you should take extreme care in choosing the materials for vacuum technology, whether it is a flange material, whether it is a seal material, whether it is a chamber material. You have to keep track the operations in mind. You are going to weld. Okay. While welding, carbide precipitation should not take place, then it will rust. Some amount of chromium it comes out, and the rest of the area if it is deficient. So, when to use high carbon steels, when to use low carbon steels, it is a metallurgical mechanical engineer with good idea of machining and welding. These fabrication issues we will see in the next class, because fabricating vacuum components, vacuum chambers is not same as high pressure components, and outgassing properties have to be chosen. Polishing has to be done heavily. High pressure vessels you need not polish much, but in high vacuum applications you have to polish it to optical level. So, the real cost of the chamber is towards the last process when you are polishing it, not when you bend it in the form of a cylinder, when you weld it, make the flanges, couplings, flanges. That is a mechanical strength calculation you will have to do following some ASME code we will see in the chamber design. But real problem comes, how are you going to machine it? And while machining, you should be careful. You should not sweat much. If one drop of sweat falls and by mistake you connect it to vacuum chamber, and it is going to create a billion cc of gas, water vapor later, you will never get vacuum. So, in vacuum technology, cross related problems are there with respect to materials. You have to be very careful. So, starting material, if you have taken very good polished material, it is better. So, you have to take a decision, but if your budget is not allowing, then same polished material take a less thick and use stiffeners outside. Outside it can be rough, it may be looking dirty from outside, but inside it should be good. It is valid for a person also. Person may be looking good, but if inside if it is good, it is good. Okay. Everywhere in vacuum, the innermost surface should be very clean. Outer surface has no meaning. Okay. That is very important. Then seals, Viton is the ideal thing, but some butane with different varieties of polymers are also available, but nowadays it is tendencies towards Viton seals, because they can be baked and degassed and reused also up to 150 degrees centigrade. Greases and oils should be chosen with low vapor pressure. Aluminum is ideal, but unfortunately it cannot be welded. Lot of research is going on with aluminum alloys with welding technologies. If it comes and if the temperatures are less, then aluminum chambers are definitely good. It may get look like oxidized, dirty looking outside, but inside it will degas much less. So, we will discuss these degassing issues when we go for vacuum chambers and in various process applications. If it is a chemical or pharmaceutical applications, we may not bother about outgassing from the surfaces. We have to bother about the materials which will not be attacked with these chemicals. So, depending on the issue, application issue, you have to choose the material, but finally it is only 1 bar pressure difference, not much. So, mechanically if you make that design, you following ASME codes for external pressure vessel of 1 bar atmosphere change, it is good enough. And if you want to reduce the thickness, use the stiffeners outside. And ceramics, very high quality ceramics need to be improved further still, because ceramics are going to be used in futuristic high vacuum based technologies in energy sector, nuclear sector and various other sectors, particularly semiconductor, electronic circuits, etc. So, there is a lot of research going on in metals, alloys, ceramics, glasses, greases and seals to make vacuum technology towards ultra high vacuum, ideal for high tech applications. With this discussion, we will go for fabrication issues, then degassing issues, and finally, we will make a system out of it before we venture into troubleshooting or real applications, and then we will come back to design reiteratively again and again, but keeping in mind the central issue of choosing proper material for proper application. So, with this, let us end this talk on metals, alloys, ceramics, greases under the name vacuum materials. So, if you want more information, we can discuss, you can make a call to me anytime. Thank you very much.